Hi, this is Dr. Simon Romero. I'm here to present you the video tutorial for iterated integrals and Fubini's theorem. The idea is we're going to try to compute double integrals over rectangles without using Riemann sums. And for that, we're going to use something that we did in calculus of one variable, that is volumes and cross sections. So a cross section is the intersection of a plane with the surface. So this is a cross section, and in particular we're going to focus on cross sections that are aligned or corresponding to a particular point in the x-axis. So what we saw in calculus of one variable is that the volume was going to be the integral from a to b of the area of the cross sections. Now you can think about this, or one of the reasons why this is called an integral is because the thing that you are doing is you are integrating all the cross sections from A to B, and that will, all the cross sections together will give you at the end the volume of the surface. So notice that a of x is a function that gives us the area of the cross sections for each x. So if we can find a formula for the area of the cross sections, then when we integrate that, will give us the volume. So that's what we're going to do here in our case. So we have a rectangle, and we are trying to compute the volume underneath the graph of the function and over the rectangle. So the thing that we're going to do is we're going to take the rectangle and we're going to fix y. And our objective is trying to find the area of this green thing. But notice that that's just the area under a curve. So the only thing that we have to do is take the integral from a to b of f of x y dx. So the thing that we're saying is the variable x is moving from a to b. We hold y fixed, and this green area is going to be the green area that we're going to compute, but that's just going to be holding y fixed, and we're going to integrate with respect to x this function. Once we have this area, the volume is going to be the integral from c to d of the area of y. This is by the formula in the previous slide. We obtain the volume by integrating all the y cross sections from c to d. So, but remember that a of y was just this green integral over here, so I put it over there. And notice that this is one way that you can compute it, but we could do the same by just, instead of fixing y, fixing x, and these are the area of the cross sections with respect to x, and then integrating the area, the a of x with respect to x. So notice that in this case we are getting two integrals more or less in the same way. So an iterated integral is an integral of this form. An integral that first you integrate with respect to with one variable, and then with respect to the other one, a function of two variables. Notice that these are the integrals that we were talking about. So we have Fubini's theorem. Fubini's theorem says that if you have a continuous function over a rectangle, then the double integral is just going to be the iterated integral. Let me rephrase it. If you have a double integral over a rectangle, the only thing that you have to do is pick a variable that you want to integrate first. Then you put that integral inside, and you put the limits of integration in the corresponding integral. And then after you finish this one, now you do the other variable with the corresponding limits of integration. You can do it this way, or you can do it the other way. First integrating with respect to y, putting the limits for the y, and then integrating with respect to x and putting the limits for the x. So Fubini theorem says that the double integrals over rectangles are just iterated integrals. Note that in this particular case, the order of integration does not matter. Let me give you an example. So suppose that I want to compute this double integral over this rectangle. So I choose one. Let me just choose x, the integral that we're going to do first. So this is, I'm going to integrate with respect to x, this function. So y is for right now is just constant, and I'm going to integrate from 0 to 4 dx. Then after I do that, I'm going to integrate with respect to y. I'm going to go from 1 to 2. So I'm going to go inside out. So I am going to compute first the blue integral. So in this case, I have this particular integration. This is a constant, and blah, blah, blah. Then I plug in, I take the difference, the evaluation at 4 minus the evaluation at 0, that gives me this. And that at the end will end up being something that only has y's. Remember, the x disappear once you evaluate. Once you have this single integral with respect to y, you integrate again, and then I integrate with respect to y like a normal integral. Then I evaluate at 2 and 1, and I end up with 6. So let me just show you that you could have done it the same way, but now first choosing y and then x. If I choose y instead of x, I have to put inside the limits for the y and then outside the limits for the x. Integrate first inside out, so I integrate first the integral that is inside. I obtain this, then I simplify this, I obtain something that only has x's, and then I integrate with respect to x from 0 to 4. And I obtain also 6, and that's the answer for this problem. And this finishes this video tutorial. Thank you very much.